Hello, STEM 1 students. I want to teach you a little bit today about the connections between what you're going to be learning in algebra and what you've just finished learning in physics, and also kind of tying it into our next unit project. So you're going to see some of this stuff be like, well, didn't we just do this in physics? And yeah, the answer is yes. That's the cool thing about this class is it really connects the two ideas. So what I want to look at is in question number 1 here, just to give you an idea of my plan for the video. We're going to go through 1 and 2 together. We're going to talk about this concept on the back, and then you're going to be trying these last 2. And then at the last part here, you will have an opportunity to vary your assignment based upon the way you want to showcase your learning. So the first idea is that when we have a line that looks like number 1, in math they call this the slope-intercept form. And so you see this right here. This form is, this number 1 is an example of that. And so slope-intercept form, if you want to write this in the heading somewhere, slope-intercept form is an equation that is written as y equals m times x plus b. And it's almost it's really the same thing you've been doing in physics. It's just mathematicians do it more general, and physicists make it like really specific to the example that they're working on. So notice y is our dependent, m is our slope, x is our independent variable, and b is the y-intercept. And so you can kind of see the way this is set up really matches the physics models that we've been working with for position and time. So let's just say we didn't know what this graph looked like, and some of you might and some of you might not. You can always figure out what a graph looks like by choosing inputs and evaluating the outputs. So I'm going to just pick a few inputs for my x values, and I typically choose numbers close to 0. I also like to choose numbers that are at least have one negative value and the number 0, because 0 is always easy to evaluate. So when we look at this one, what we're doing is we're taking the right side of this expression, and then we're just going to replace x with the input. So in this case, we're going to take 6 times -1 and then subtract 2. So that's going to give us -6 minus 2, which is a -8. All right, then we're just basically going to do the same thing all the way down. So I'm going to copy this and paste it. And then basically all we're going to do is change that input number as we move down to each new input. So this will become 6 times 0, 6 times 1, and 6 times 2. So 6 times 0, 6 times 1, 6 times 2. And so 6 times 0 is 0. Take away 2 is -2. 6 times 1 is 6. Take away 2 is 4. And 6 times 2 is 12. Take away 2 is 10. All right, so it looks like to make our outputs fit, these are our y values, we're probably going to have to scale this by 2. So I'm just going to put 2, 4, 6, and just kind of scale that graph accordingly. And then I'm going to do the same thing in the negative direction. Whatever you pick for your scale on the positive side, you have to use that same spacing on the negative side. So that becomes a -6. All right, my inputs are relatively small, so I'm just going to say, 1, 2, and then I'll put -1 over here. So our first order pair is at -1, -8. That's going to go right here. Our next one is at 0, -2. Oops, that's supposed to be a -8, isn't it? Let me change that. -1, -8 would be down here. I'll add on to my scale. The next one is at 0 is my input, -2 is the output. So that's going to be right here. And then the next one is 1, 4, which is right there. And the last one is 2, 10. All right, again, since we were given an equation, when we start with the math model and create points, that forces them to all be linear here when they're in the form y equals mx plus b. And so you can kind of see if this were a car or an object that we were tracking the position for, it starts right here at -2. And Mrs. Stuckey just got through telling you that's your initial position. Okay, the other thing to notice is that since it is a positive slope, okay, it's a positive slope, that means the object's moving away from the motion detector, not towards it. So based on the way this is set up, I'm going to look here. The m matches 6, so our slope is 6. The y-intercept is this always the number you add or subtract. So in this case, the y-intercept is -2. And so you notice we started at -2 and our slope was 6, +6. Okay, we're going to do 2 in a little different order just because I want you to see that plotting points works. It's not as time efficient as using the slope and the y-intercept. So at this time, I'm actually going to start with recording my slope and my y-intercept. Okay, and I want you to look at the options here. We're going to do this option first, just so you can see how to come up with the graph. This says to plot your y-intercept and then apply rise and run. So let's start with our y-intercept. Let's start with this 4. My y-intercept is at 4, so I'm going to go up to 4. And as long as I'm scaling by 1s, I don't really have to indicate on the graph what my scale is. Mathematicians assume it's by 1 unless you state otherwise. So we're going to start at 4. And my slope is negative, so that means from left to right it's going to go down. Well, how much is it going to go down? Well, slope can be thought of as change in y over change in x. And if it's negative, I'm going to encourage you to get in the habit of putting the negative number on the top of the fraction. And that way you're always going to be running to the right, because a lot of students learned this as rise over run. So the change in y says we're going to go down 1. So I'm going to start right here. I'm going to start at our initial position. And I'm going to go down 1. And then I'm going to go over, the change in x is 3. So we're going to go 3 to the right. You wouldn't want to go to the left, because if you do both of them negative, look what happens. The line actually ends up with a positive slope. And that's not what the equation tells us. So we're going to start at our y-intercept. We're going to go down 1, run 3. Down 1, run 3. And I'm just going to repeat that several times to establish a pattern. And draw a line through those points. They should all line up. And as long as I'm counting by 1s, I don't really have to put a scale in. So let's just verify a few of our points. So this is an input of 3. Let's just see what happens if we pick an input of 3. So I'm going to use the right side. I'm going to say -1/3 times my input of 3. And then we're going to add 4. So PEMDAS says to evaluate the multiplication first. Well, I notice the 3's cancel. So I get -1 plus 4, which means my output or my y value should be 3. Well, if you look, this point, when the input is 3, the output or the y value is also 3. So that tells me that the shortcut graphing method we used worked pretty well. Okay, so let's check one more point just to make sure. Let's see an input of 6. According to this, an input of 6 should have an output of 2. So let's see if that works. So negative 1/3 times 6, my input, plus 4. I'm going to put that 6 over 1 and then just simplify. So 6 divided by 3, that reduces to 2 and 1. So we get negative 1 times 2 is negative 2. Divided by 1 is still negative 2 plus 4. So an input of 6 is going to give us an output of negative 2 plus 4 is 2. Well, look at this point right here. It's exactly the same thing. Okay, so there's more than one way to come up with your graph. You can make a chart. You can also just use, this shortcut right here, which is what I would start encouraging you to do. You know the y-intercept, you plot that first, and then you treat the slope as a rise and a run. If they don't give you a rise and a run, like this one here, you could treat it as, you can just say it's, well, let me give an example here. Let me scroll forward. So like here, you could treat negative 5, if you wanted to do a rise and a run, you could say for it's going down 5 for every 1, just like we did in physics with our unit slope. So it's really easy to turn that into a rise and a run just by putting a 1 underneath it. Dividing by 1 doesn't change anything. So you'll be trying that one here shortly. All right, so if you flip to the next page of your packet, I'm going to have you pick a vertical line. Actually, we'll do this part together. Let's just draw a vertical line, and I'm just going to randomly place it. It doesn't really matter where, but I want it to fit on your grid system so that it's a nice whole number. So I'm just going to pick my vertical line right here. Okay, I'm going to have you put points just on 3 spots, and I'm just randomly choosing right along that line. And then we're going to document what those ordered pairs are right next to it. So my first ordered pair that I plotted was back 4, up 1. So I'm just going to want you to record that next to that point. So negative 4, 1. And then this point above that was back 4, up 4. So I'm going to say negative 4, comma 4. And the last one that we did was back 4, down 4. Let me double check that. 1, 2, 3, 4. 1, 2, 3, 4. Yep. Negative 4, comma, negative 4. Okay. So why did I have you do that? Well, let's look at what happens. Oh, I was going to put them over here. No big deal. We'll just list them on the graph instead. So don't worry about these blanks. So if you notice, it says, and observe that an input of, well, what was our input here? The x value was negative 4. An input of negative 4 actually creates 1, 2, 3 different outputs here. So we're going to say it creates multiple outlets, or outputs, I meant. Which part of the ordered pairs stayed the same? Well, if you look at your ordered pairs, only the x-coordinate didn't change. Therefore, when we write equations of vertical lines, it's always going to be x equals whatever that number is that it passed through. So, for example, Desmos, if I did x equals 5, it's going to draw a vertical line through 5. If I did x equals negative 3, it's going to draw a vertical line through negative 3. X equals 8, they're always going to be vertical lines through the x value of 8. And it's that simple. So in this case, the equation of this line would be x equals whatever number it went through on the x-axis, which was right here, -4. That's an equation of a line. It's not just a point. It's the entire line is written as x equals -4. So would you ever see this with a position time graph? Well, think about it. This would mean that a given time, a time of, in this case, -4, which doesn't make sense, but like even on this side, a time of, say, 5 seconds, that means the car would be in multiple positions after 5 seconds. That doesn't make sense. So vertical lines are not functions, but they can be graphed, and it's really simple. You just put x equals whatever number they go through. Okay, so in class right now, your job is to finish numbers 3 and 4. Show them to me or a teacher so we can see that you understand this topic. Okay? Then your assignment, you have a choice. You can either, you can either get the graphing worksheet and complete that. I think there's like 12 graphing ones. They're pretty short. They won't take you a ton of time, but there's quite a few to practice. The second option is that you can create your own equation in slope-intercept form. In other words, like something like this: y equals some slope, and then times x, and then plus or minus some number. You can create that. And what you're going to do is you're going to record a short screencast explaining how to graph it, and then upload it to Classroom. Okay? Whichever option you choose. These are due for class time Tuesday. I'll put due Tuesday, start of class. Okay? I don't care which one you do, but some of you like to do more of the talking side of it and explaining, and some of you would just rather do the practice. So either option is fine. At this point, go ahead and do your in-class practice, show it to a teacher, and then if time allows, you can start the assignment. Let me know if you have questions. Thanks. Bye.